Welcome to today's session on compressors using SimScale. SimScale in general can handle rotating machinery applications including turbochargers, compressors, pumps, water turbines, propellers, and fans. Generally, compressors are used in many industrial applications including automotive industry for turbochargers or compressors, industrial usage in terms of compression of gas, and in aerospace as well. There are other applications where compressors play a major role, including HVAC, refrigeration, cooling and climate control, manufacturing, and medical industries. In today's session, we'll be looking into the fundamentals of compressors, and by the end of the session, you will be able to understand how to predict the efficiency of a compressor, what are the key criteria to check whether the compressor is working at its best efficiency, and also understand how to simulate such as compressor simulation using SimScale. A compressor in general has three different sections. The inlet section, which takes up the low velocity flow. The impeller or the rotor, which imparts the kinetic energy to the fluid. And the outlet section, which acts as a diffuser. These three main roles are played by the compressor. It takes in a low velocity gas. With the rotating component, it imparts the kinetic energy to the fluid, and at the outlet, the fluid is allowed to expand, so it can be tuned to actually get a specific flow rate. A compressor can be defined or identified using several parameters, but the key parameter here is a compressor map. And this explains the best efficiency range the compressor can work in. It includes two main criteria or phenomenon in compressor dynamics, which is surge and choke. A surge is a condition where the compressor is not receiving enough fluid to actually run through the system. It's almost like a compressor is thirsty. On the other end, with high flow rates, we see a choking condition. A choking condition is where the compressor cannot work above the efficiency which is designed for. This usually is identified by a drastic drop in pressure ratio on a compressor map with different RPMs. In the next few minutes, we'll be learning how to simulate such a compressor and find out these surging and choking regions, and also find out the best efficiency of the compressor. To simulate a compressor, there are specific CAD requirements for any CFD tool. Within SimScale, you will need two different volumes to simulate a compressor. The first one is a combination of the inlet, the rotating section, and the outlet or the diffuser section. All these sections should be merged together to form the volute of the compressor. Since the compressor has a rotating region, we would need to define an overlapping volume that defines the rotating region within the compressor. It can be an offset of the blades or the rotating part in your compressor, or a simple cylinder which is axis symmetric. When these CAD components are ready, you should be able to simulate this using SimScale. Let's look at a typical compressor simulation, understand what results you can get out of the simulation, and see how you can set up such a simulation using SimScale. Here we are within the SimScale's post-processing scene, and a compressor simulation usually writes out a bunch of key variables, including the velocity of the fluid, the pressure inside the fluid domain, the Mach number, density, and other parameters related to the turbulence. Here we are looking at the Mach number plot within a compressor, which has a flow rate of about 0.2 kilograms per second. In this example, the compressor is rated from 70,000 RPM to 80,000 RPM, and we are looking at the results of a 70,000 RPM case. You can look at the low flow rate regions where the compressor acts exactly as expected, where you'll be able to find design insights in terms of tip speeds, also see the distribution of velocity and Mach number around the blades and the diffuser region. This is a good example of a compressor working at a good efficiency range. Hence, we don't see any abnormal flow characteristics. If you want to find out until which the compressor can act normally, you can run this for multiple flow rates. In this case, we have run the flow rates ranging from 0.2 to 0.32 kilograms per second. In order to understand a choked flow in a compressor, you should be able to see and plot the Mach number for different operating points. Here, let's try to compare the simulation of the low flow rate regime with the maximum flow rate that we have simulated. Thanks to the compare mode in SimScale, we should be able to simulate and compare results of two different simulations on a side-by-side view. On the left, we have the low flow rate case with 0.2 kilograms per second, and on the right, we have the case with 0.32 kilograms per second. You can immediately notice that the case on the left is not choked due to the continuous flow in the compressor, while on the right, we have a drastic change in the flow rate or the velocity near the diffuser. Here we have the color mapping ranging from 0 to 1, which means anything over 1 is a choked flow. And this is clearly seen here near the diffuser that the flow jumps between a low flow rate to a higher flow rate. This indicates a choked flow in your compressor. In addition to this, you can also look into the density variations within your system to compare and identify the flow characteristics. You can also look at the flow tip speeds on the blades of your compressor, and in the density changes as well. This is clear that near the diffuser there is a choked outlet. Apart from the visual feedback that we can get from a CFD simulation of a compressor, we can also look into the efficiency parameters like the pressure ratio on a 2D plot. This is available as part of the results for each simulation, and since we have run a series of operating points, you will also ultimately get a plot that compares the total pressure with respect to the flow rate. Here you can see the change in pressure with respect to the flow rate, and this can be easily downloaded as a CSV file for further post-processing. With the total pressure at the inlet and outlet available as a direct output, we can easily plot the pressure ratio with respect to the RPMs that we have simulated. In order to look into the isentropic efficiency, you will have access to the total temperature changes with respect to the flow rate as well. That can also be written out as a 2D plot or a CSV file for further post-processing. This covers the compressor simulation and gives us enough design insights to make sure your compressor is working in the best efficiency range. A quick post-processing of these parameters can give you a compressor map that can be seen on this slide here. For 3 different RPMs, we have now simulated various operating points with respect to different flow rates. Now you can see a definite drop in the pressure ratio on the last few flow rates, which indicates the choke line of the compressor map. That wraps up the compressor simulation using SimScale and analyzing the results for your best efficiency range. We'll see you in the next one. Take care.